Давай.
So hello everybody. What we're going to do today, my plan is to do one application of reduction. So we've seen the reduction theorem last time. And so here is one application of reduction. It goes under the name of toric manifolds. And perhaps some of you have seen it from more like complex geometry standpoint, and we're going to see it from symplectic geometry standpoint today. And this approach, right, of course, toric manifolds is a big topic, but this approach to toric manifolds is due to Eugene Lerman. And that's because we'll be using some kind of upgrade or some more complicated version of symplectic cutting that you saw in the problem set. So to start with, let me talk a little bit about tori, because we'll be doing reduction under the actions of tori. And here is what we start with. So we consider a real torus of dimension k. So we're going to have tori of dimension k and n, and I'll probably be mixing them up from time to time. I invite you to catch me. And okay, so that we start with a torus of dimension k, and let me tell you, or let me remind you, what is the integral, or the other name is covate lattice. So let's call it lambda, and these are vectors in the Lie algebra of the torus, such that the exponential map applied to V is equal to 1. So in other words, these are all preimages of the unit element, of the neutral element of our group under the exponential map. And concretely, how does it look like? So this lattice, I mean, here I must say I have difficulties. I usually have difficulties with signs, but today, in addition to difficulties with sign, I have difficulties with imaginary units and 2 pi's. So let's say I identify this Lie algebra with 2 pi I times z to the power k, because the exponential of 2 pi I is 1. And of course, here, this means that I have a convention, at least for time being, that the Lie algebra of S1 is the imaginary axis, right? So now suppose I'm given some element of the lattice lambda, and then I would like to associate to this element a group homomorphism from the circle to my torus tk. And it works as follows. Suppose that here I have an angle theta, an angle representing an element of S1. And here I must say, so it's kind of inconvenient that the circles, they have this circumference equal to 2 pi. Of course, I know that's a classical fact, but well, I mean, it makes it slightly more painful, or maybe I haven't invented a good notation. So I map it to the exponential of theta over 2 pi times v, right? So so it's easy to check that this is well-defined group homomorphism. And in fact, all group homomorphisms from S1 to TK, they are like that. So that's why sometimes this lattice is called covate. Covate, this means covates are usually homomorphisms from S1 to the torus. And integral, that's the definition that I gave you. So that's the preimage of the group unit. So both things are equivalent. So now I described all the group homomorphisms from S1 to T to the power K. Now maybe just one small remark. So this group homomorphism phi V is injective. So what does it mean? So this means that theta over 2 pi V is not in lambda if theta is between 0 and 2 pi. So there is no multiple of V with a proportionality coefficient which is between 0 and 1, such that the corresponding vector will be in lambda, right? So that's where the homomorphism phi V is injective. So we're going to see examples.
Anton, isn't 0 in lambda?
Sorry, no, but I say theta is bigger than 0 and smaller than 2 pi.
But V may be 0, isn't it possible?
Right. So V may be 0, okay, but then certainly the condition is not verified, because for any theta this multiple will be in lambda, and the homomorphism is not at all injective, right? Because it maps all the circle.
That's what I
yes,
mean.
but I think okay, yes, but I think what I'm saying is still correct, right? So I'm saying phi V is injective if, maybe if, that's the key word.
If I didn't see that. I misunderstood. I thought you were saying it's injective. Okay. It's okay.
Yeah, so for the homomorphism to be injective, so those multiples of V, they should not be in lambda, right? So V is in lambda, 0 is in lambda, that's all good, but everything in between should not be in lambda, because otherwise, right, there would be no injectivity, there would be another preimage of 1, right? Okay, good. So maybe we can extend this remark in the following way. Suppose I consider several elements of lambda, V1, VL, and I construct a group homomorphism. So they define a group homomorphism from T to the power L to T to the power K. So how does it work? Of course, it works just in the same way as before. So I take those angles, theta 1, theta L, so they parameterize L circles, and I map them to the exponential of 1 over 2 pi, and here I take a sum over A from 1 to L, theta A, VA, right? So it's easy to see, this is again a group homomorphism. And we are interested in a question. Oops. So I haven't changed the format in the right way. So, and we are interested when this group homomorphism is injective. So let me state the condition, and then you tell me whether it's clear or not. So first of all, so there are two conditions. First of all, we want those V1, VL be linear independent. If not, of course, there would be no injectivity. But then there is the following condition, which is exactly the multidimensional analog of this condition here, right? So so let me state it in the following way. So we want 1 over 2 pi sum over A, theta A VA to be in lambda. It should be equivalent to all thetas to be in 2 pi z. Or, of course, maybe it's a bit more elegant, theta over 2 pi in z. Let me give you examples, and we'll see how it looks like. So, of course, I'll be doing two-dimensional examples because that's easier. So that's my Lie algebra T of the torus. That will be my integral lattice lambda, or the covariant lattice. Right? So this is lambda, and now I'm choosing two vectors v. So this will be v1, and this will be v2. So what's your judgment? Is the condition verified? Of course, the first condition is clearly verified. V1 and V2 are visibly linearly independent. Now, is the second condition verified? Let me do the drawing, and in the meantime, you can think of your answer. So I'll do this drawing for you, which is supposed to be suggestive. So what's so is it okay? Those two vectors, do they define a group homomorphism from T2 to itself in this case, right?
Yes, it doesn't contain any points inside.
Yes, that's right. That's here. You just see that all those combinations of V1 and V2 with coefficients between 0 and 1, right? So that's this shaded region, this parallelogram. So there are no red points inside, so there are no lattice points inside, and this means we are injective. So this is good. So now another example, and well, of course, you can guess there it's not going to work. So let me try to draw it, right? So that's again my integral lattice. I'm taking the first vector, v1, and I'm taking the second vector, v2, a bit similar, but in a somewhat different direction. And now it doesn't work because there is this red point in the shaded region. And in formulas, this means the following. So, right, this is 1/2 of v1 plus v2, which is in lambda. And so this means that if I choose theta1 equal to theta2 equal to pi, that point is mapped to the group unit, and I don't have injectivity. I have a non-trivial element of my torus, so the induced map. So the induced map of T2 to T2 is not injective. Okay. Yeah. So maybe the last remark on that. We can also reformulate. We can also reformulate this statement as follows. So we can. So of course we want the L to be linearly independent. And the second condition we can also state like this. I mean, sometimes it perhaps more handy. So you consider a lattice spanned by V1, VL, and you check that it is the intersection of the real vector subspace spanned by the same vectors intersection with lambda. That's exactly what we are checking. And in the case of L equal to N to K, right? So that's a somewhat special case. And in this case, we can also say that V1, VL is a basis of the lattice lambda. So that's all. It's all the same. For instance, in our example, which worked in the first example, V1 and V2 is a basis of this square lattice. And in the second example, V1 and V2, they failed to give a basis because if we generate a lattice, this would be proper sublattice. So in particular, that fat red point not going to be part of the sublattice. So that's how it works. All right. Sorry for like bugging you with all this stuff, but we'll need it very soon. So let me add one more thing. So these are coveights. Let me recall that there is also a weight lattice. We're not going to use it too much today, but later on in the next classes, we're going to need it all the time. That's why maybe it's good to introduce the notation now. So so that's the weight lattice. It's sitting now inside the dual, inside T star, the dual of the Lie algebra. In our case, it's simply isomorphic to z to the power k. Elements here are k-tuples of integers. And to such a k-tuple of integers, we associate a map in the other direction, a homomorphism from our torus to S1, right? Coveights, these are homomorphisms from S1 to the torus. Weights are homomorphisms from the torus to S1. And the formula is like this. So we have an element T1, Tk of our torus, where these are all complex numbers of absolute value equal to 1. And this image is simply equal to the product of Ti to the power lambda I. Now, maybe an interesting remark. There is a duality between weight and co-weight lattices. And this duality is taking values in Z. And how does it work? Well, one can guess. So suppose we have an element of our integral lattice, our co-weight. So we organize a homomorphism from S1 to TK, phi V, and then we compose it with a homomorphism psi lambda from TK to S1. So this is, of course, a homomorphism from S1 to S1, this composition. And so this composition, right, if we start with an angle theta, so all the homomorphisms from S1 to itself, this is just multiplication of theta by an integer, right? So there are no other homomorphisms. So, and we assign to the pairing, to the duality between V and lambda, this very integer, right? So this is a perfect duality between those two, natural perfect duality between those two lattices. All right, so this half a page, I don't think we need it today, but the rest of it, this theory of co-weights and of injectivity, this plays a crucial role in what we're going to do. All right, so now we have one more prerequisite. I will bug you a little bit more before going into symplectic geometry and reduction. And so this is the theory of Descent polyhedral sets. So what are those gadgets? So first of all, let me give the following definition. So delta, and this delta will be inside T star. We're going to consider some subsets of T star. Is a polyhedral set if it is an intersection of a finite number of half spaces. So delta is an intersection from 1 to k, and I mean this k, right? At the moment it looks a bit sloppy that I'm using the same letter, but in fact that will be the same letter as the dimension of our torus, right? Of HA and HA. Here I must say I tried to fight with my signs without much success. So HA is of the following form. It's lambda VA, the pairing, is greater or equal to mu A, where VA is an element of the lattice, which is sitting inside T. And here I'm using the pairing between T and T star. And nu A is just a real number. So in other words, HA, these are half spaces. Sometimes it's also convenient to use HA0 for the corresponding hyperplanes. So, or affine hyperplanes. So here we have an exact equality. So here this is an inequality, and here we have equality. We also, on some occasions, need HA plus, and that's where the inequality is strict. Okay, so let me give you a couple of examples.
Sorry, Anton, what is new? Are you saying that new exists such that this is fulfilled?
Oh, they just all HAs. They are half spaces like that, defined by a pair of VA and nu A.
Mm-hmm.
So you can say, maybe right, maybe I should say, so HA is H of VA nu A. So you're given an element of the integral lattice, a covariate, and a real number, and they define for you a half space inside T star. So let me give you a couple of examples. Perhaps it would illustrate it. As usual, my examples are two-dimensional, right? So this is my T star, and I'm looking at this half space, right? So here the pair is V. I can choose, for instance, 1, 0, and nu equal to 0, right? So that's oh, sorry, 0, 0, 1. Yeah, that's wrong. 0, 1. 0, 1. So lambda 2 is bigger than 0. That's my half space. Okay. And one more example, which will be very, very useful for us today. So let me try to draw it. So it will be this triangle with the right angle. So it is defined as an intersection of three half spaces, right? And what are the corresponding data? So V1 is 0, 1, nu 1 is 0, V2 is 0, 1, nu 2 is 0, and finally V3 is minus 1, 1, and nu 3 is whatever it is, rho bigger than 0, and rho is the coordinate of those points, right? So sorry for bugging you with this elementary geometry. Maybe some remarks. So some remarks about it. Okay. So maybe the first remark, if delta is compact, so then it is a convex polytope, and it is equal to the convex hull of its vertices. So what do I want to say, right? Maybe instead of proving it in general, just let me explain in the example. So you see in the example 2, this is a convex polytope, right? This triangle. So these are the vertices. Let me call them alpha 1, alpha 2, alpha 3. And everything inside the triangle is obtained as a convex combinations S1 alpha 1 plus S2 alpha 2 plus S3 alpha 3 of the vertices with S1 plus S2 plus S3 equal to 1, right? So these are convex combinations, and this is always like that if this intersection is compact. Right. Now, maybe a somewhat more intricate remark, which will be useful for us. But so this one is somewhat more complicated. So delta is a disjoint union of delta i's. I think there is some question, right? Or let me see. Okay. Yeah, of course, that's a Jude. That's a very, of course, your question is very well justified why I'm doing all that, right? But wait, let's say 5 minutes. Wait 5 minutes, and we go back into symplectic geometry and reduction. So, I will not be doing now simplicial homology. So in principle, yes, of course, that might be one direction, but that's not what we are doing. So this story of Torre and covates and this story about polytopes, these are two prerequisites, and then they will culminate in some symplectic moment map construction that I will show you very shortly. But okay, so stay with me. All right, so delta is a union of delta i's, where i's are subsets of the set 1k, and this delta I is defined in the following way. So for a in this subset I, you consider the intersection of the corresponding hyperplanes, and then you intersect it with the intersection for the other indices, which are not in I, of how did I denote it? Of H pluses, right? Of the open half spaces. So some of those delta i's, they may be simply empty. So let's, for instance, redo this example with a triangle, just to show how this stratification of the polyhedral set looks like. And you will see it will be, so everything I'm doing now is very, very useful for us. So first of all, there is the interior of delta, and this is delta empty. So I don't choose any indices. So that's the intersection of those open half spaces, right? So that's the interior. Of the triangle. So then let's do one of the sides, right? So for instance, this side is delta 3. So delta 3, right? This means that for this hyperplane, the equality is simply satisfied. That's why we're sitting on that side. So that's the side one of the sides. So the other deltas with just one index, they will correspond to other sides. Now, what about this gadget, the corner? So this is delta, I believe 1, 3. So that's one of the corners. And finally, what about delta 1, 2, 3? So what is it? So now all the inequalities are just equalities. Then what is the corresponding delta 1, 2, 3? So tell me. Or you can just type in the chat. So what is this? What is this thing? Oh, it's empty. Sorry? Yeah. Yeah. That it's empty. That's because the three straight lines, they never intersect, right? So there is no intersection point of those three straight lines. Okay. So now the key definition in this part. So delta is called delsant if phi I. So this is a phi defined by so that's the homomorphisms of tori defined by VA for A in I is injective for all I. Such that delta I is non-empty. So you see, it's a sort of complicated definition. So let me. So you're going to work with it a lot in the next problem set, but let me still illustrate it a little bit in my example with a triangle. So
have you defined phi I already?
Well, phi I, yeah, maybe yes. Maybe we did not properly define phi I, right? So phi I again, right? We defined homomorphisms, right? So we defined homomorphisms from TL to TK by finite families of vectors in lambda, right? So right, that's this homomorphism. So now what I have in our setup. So there is this set of VAs. So there are K of them. But now I'm choosing a subset I of this set from 1 to K, and I'm taking the corresponding VAs. So maybe I here write it again. So what I'm doing is the following. So so this, yeah, let me. So this will be on the next page.
Well, it's the thing you defined before, where the thetas are 0 if A is not in I.
Yeah. So this will be. So this will be a homomorphism from so it will be a homomorphism from TI.
Yeah.
Sorry, that is all very bad what I'm doing. Right. Okay. Yes, that's what that's what I feared. Right. So now we introduce the second torus, Tn. We introduce its Lie algebra, isomorphic to Rn or I or N, and inside it we have lambda. So all my apologies. So now everything is sitting inside Rn, and there are k hyperplanes, half spaces, which define these those polyhedral sets. Yeah, you know, like, sorry, I'm kind of sorry, people. I'm myself getting lost in it. So here, n is equal to 2, and in this example, k is equal to 1, and in this example, n is equal to 2, and k is equal to 3. Right. Yeah, sorry, people. So, right. So phi I is a homomorphism from Ti to Tn. It takes the collection of angles theta I with theta A with A in that subset, and it is mapping it to the exponential of 1 over 2 pi sum over A in I theta A VA, and this is an element of C to the power n. So notice the following, right? Already for phi I to have chances to be injective, right? Already we know that we want I to be less or equal to J for all delta I non-empty, right? So this is a kind of big condition. So now this definition, it imposes conditions on our polyhedral sets, rather restrictive conditions. So we're gonna see it today. And by the way, that's maybe a good point to say that next time is not on our schedule, but I suggest to have, for those who want to come, some aside class on Gelfand and integrable systems. So the next week class is not part of the official program, but it's related to what we are doing, and it's an interesting aside. And everybody who wants to come is welcome to come. There will be no homework for next week's class. There will be, of course, homework for this week's class. By the way, Ian, maybe you want to paste the
I can do that now. Yeah.
Mhm.
Actually, by the way, let me just comment that I think you said the words, but it might be worth writing it down, that phi I is injective implies that I is less than or equal to n.
Yes,
that's what you said.
Yes. Phi I. Phi I injective implies that. All right. So let me just do my favorite example with a triangle and show that it is indeed Dilsand. Okay. So, right, how do I draw it? Maybe I draw a triangle which is a bit larger, just 1, 2, 5, right. So here is my triangle. Okay, so on the sides, so we have, of course, in the interior, there is nothing to check, right? So there is nothing to check because phi I is just a map of the trivial group. So phi empty is a map of the trivial group into T to the n, which is now T2. Now on the side, for instance, on this side, we have delta 3, and we have phi3 mapping a circle to T2, and this map is taken our angle theta into exponential of minus theta over 2 pi 1 1, and this is equal to exponential of minus I theta over 2 pi exponential minus I theta. Sorry, yeah, that's yeah, I think no 2 pi's. Yeah, that's this story of normalizations. Yeah, I think it is simply.
And Anton, there was a question from Jude, and I commented that it's probably a minor misprint, but maybe it's not so minor. I don't know.
Okay.
Yeah, he did ask anyway. You have got your superscripts and subscripts. Maybe it's.
Oh, sorry. Yeah, yeah. I'm
It was
kind
not
of.
me who noticed.
Yeah. Yeah, superscript, subscript. I'm sorry. Probably I'm mixing them up. All right. So this is an injective group homomorphism from S1 to T2. And finally, what happens with the conus, right? So here, probably the most interesting story is the story of the conus. Let's do a drawing, right? So that's V1, and this is V3. So how is it? Do they form a basis of an integral lattice? So that's our integral lattice. So do they form a basis? I think they do, right? And that we need to check for every corner. So so for del for phi 1 3, check that V1 V3 is a basis of lambda. And that we should do for every corner. And this shows that this example is Dilzant. So that's how we're checking it. And notice, fortunately, nothing to check for the full collection, V1, V2, V3, because simply, anyways, the number of vectors is bigger than the dimension of our target torus, T2. So kind of this cannot be injective. And this is because delta 1 to 3 is empty. So that's fine. Okay. So so most of the time today was this preparation and torturing you a little bit with relatively simple but still some kind of combinatorial stuff. So now let's do oops, no, that's not good. Okay. So now I'll show you Lerman's construction of toric manifolds. Okay, so so we start with the following data. T is equal to, or let me maybe write it this way. So T is the n-dimensional torus. So delta inside T star. Let's do the compact construction. Adjacent polytope. So an intersection of a compact intersection of some number of half planes. So let me choose M to be a cotangent bundle of T. So it has coordinates T and lambda. So T is in T, lambda is in T star, and it has the standard symplectic form. Sum over I from 1 to n, d lambda I, and yeah, let me denote the angles d theta I. Maybe theta is already overloaded, but what to do? So it has a T action which is Hamiltonian. With moment map mu of T lambda equal to lambda. But by the way, how is it you remember usually on a cotangent bundle of a Lie group, we have two actions, the left action and the right action. So, and now I'm saying there is just one. Why is that? So it's just a test question. So any idea what happens here? Why there is just one action? So what happened with the second action? Tell me. Yes? Muse?
I think it's an abelian group. So
Yeah, that's right. Thank you. Thank you for saving me. So they are the same up to sign. I think last time we defined it in such a way that they act in the opposite direction and the moment maps would be opposite to each other, but basically they are the same. So because that's indeed because the group is abelian. So no, that's because T is abelian. All right, very good. So now what we plan to do is the following. We're going to define an action of another torus, TK, on M. And this action, it factors through the action of Tn. And here we are putting a group homomorphism, right? So this map is a group homomorphism defined by this collection of lattice vectors v1, vk from the definition of delta, right? Recall that delta, the definition of delta, it involves the collection of hyperplanes, which are defined by vectors of lambda and real numbers. And now we are taking all of those VAs and we are putting them there. So it defines a homomorphism from TK to TN. So do you think would this homomorphism be injective? So just for dimensional reasons, if delta is compact, then the number of half spaces has to be bigger than the dimension of T star. So then there's just no chance that all those V's would be linearly independent. So so this group homomorphism is never injective. But that's fine. So the question is, what is the moment map? So let me give you the formula, and then I invite you to check it. That's easy to see that this is true. So mu tk of T lambda. So because the action factors through the action of Tn, basically you just need some linear transformation of the moment map of the Tn action. Let me here Tn. And I suggest the following. So this will be the following set of vectors. Lambda VA for A from 1 to K. And remember, for actions of abelian groups, you can actually add constants to moment map if you want. Add or subtract constants. And I would like to voluntarily subtract from those linear combinations which represent the moment map. I would like to subtract those constants mu A. So so this part is our choice, because the moment map for actions of abelian groups is not unique. I can actually choose the moment map tailored to my problem. All right. Okay. So now a theorem. So we define M delta to be the quotient of our space M of the cotangent bundle of the torus multiplied by the space C to the power K. And we consider the reduction at the 0 level set under the action of the torus Tk. So here, of course, we should say what is the Hamiltonian structure on Ck, but that's the standard one. And the standard Hamiltonian structure means that omega is I over 2, sum over A from 1 to K, dZa bar, and the moment map for our action is this. So that's the action of Tk. Each S1 in our Tk acts on its own copy of C. So that's what we are doing. Okay, so what are the statements? So so the statements are, and let's say, sorry, and assumptions, right? And we assume that the delta is Delzont. So then, first of all, M delta is smooth. And symplectic. So there is a Hamiltonian Hamiltonian T carries Hamiltonian Tn action. And the image of the corresponding moment map is equal to delta. Then for lambda in delta, the pre-image under the moment map of lambda is isomorphic to Tn modulo Ti for lambda in delta I and Ti being the image of the corresponding embedding of the corresponding group homomorphism under phi I. And finally, m delta lambda. The reduced space is now under the Tn action equal to point if lambda in delta and empty if lambda is outside delta. All right, so there are many statements, but probably before we start proving it, so we'll spend the rest of the time trying to prove at least some of those statements. But I would like to attract your attention to this one. So that's certainly the most important statement here. And basically it is saying that if you're given a Delzant polytope inside T star, then you can tailor a Hamiltonian Tn space with the moment map being exactly delta. So that's a very, very interesting statement. And so we now spend about 15 minutes proving at least part of those statements. And then after that, I'll spend the last 1 or 2 minutes to explain, to give even more significance to this fact. Okay, so for sure, we want to prove that m delta is smooth, because that's the key part of it. And we want to prove that the image of the moment map is exactly delta. Okay. So proof. Right. Okay. So we're doing the reduction of this direct product, right? So that's a multidimensional version of symplectic cutting that you saw in the I think that was the previous problem set, right? So for that, I construct the moment map for the diagonal action. So the moment map for the diagonal TK action on T star T times CK. So this moment map, it depends on T and lambda. These are they encode a point of the tangent bundle, and here this bunch of Z's, Z1, Z2. And what is it? So there are K components, so I should describe K components. And this is just the sum of moment maps for the cotangent bundle and for CK. So I have lambda VA for the cotangent bundle minus mu A minus 1/2 ZA square, and this is for all A. Right, so this is a K component moment map because we have a torus TK, and these are components of that moment map. So we're interested in mu minus 1 of 0, right? So what is mu minus 1 of 0? So these are, again, points T lambda Z. Let me abbreviate just to one Z. Where all those equations are satisfied. Let me write it in this way. And this is for all A. Right. First of all, observe that T does not participate in the equation. So no conditions are imposed on T. We can actually spell it out as equations on lambda, right? So this is equivalent to lambda VA equal to mu A plus 1/2 ZA square, and simply greater or equal than mu A. So whenever you have a set of lambdas which satisfies these conditions, you can always find Z's and T's which would also satisfy, which would fit in those conditions. So this is already good because we now see that lambdas necessarily belong to delta. Right? So if lambda is outside delta, so then we cannot find the point of the form T lambda Z. And if lambda is in delta, then we can necessarily find the point of T lambda Z. Now, here is a claim. So the TK action on the level set is free. And recall that we need for the quotient to be smooth. So if the action is free, then the quotient is smooth. And actually, here I'm saying it's smooth and symplectic, but symplectic is automatic, right? Symplectic is automatic from the reduction theorem. And smooth, we don't know, right? Because smooth, for that, we had some assumptions. We had an assumption that the action on the level set is free. That we don't know. And that's probably the high point of today's class. So now we're going to see that it is free. It's very easy, but still it's kind of interesting. So suppose we have a point T lambda Z inside the preimage, right? Of course, we know that this means lambda is in delta, right? Lambda is in delta. Now, let's say lambda is in delta, but then lambda is in some particular delta I, right? Or sorry, I never know, right? Should I write subscript or superscript? So lambda is in some particular delta I. So, so now if A is not in the subset I, then this means that lambda VA minus nu A is strictly bigger than 0, right? And this means that ZA is non-zero. And this means that the action by rotations so this action is free. So right, we have a torus TK. It consists of many circles, and the circle S1 with the index A, it just rotates the A, and this rotation is free, of course, if we are not at the origin, right? So all those circles with indices which are not in I, they rotate their ZAs freely. Now, what happens if A is in I? So then, of course, those ZAs are 0, right? Those ZAs vanish. But we know that the corresponding phi I, which maps the torus Ti to Tn. So this map is injective, and Tn, it acts on the cotangent bundle simply by whatever left shifts or right shifts, whatever was the good sign, and this action is free. So therefore, for all those components where ZA is 0, we know that the rotations on the other side, right? We consider diagonal TK action, right? And so for some of the circles, the action is free on the second component, and for the others, it's free on the first component. So for each point in the preimage of 0, you can split the circles into two families. One family acts freely on the first component, the other acts freely on the second one, but in total, they always all act freely, which is amazing. So that's the conspiracy of all our definitions, what we needed, all this work, just to say that now the TK action on the fiber is free. Right. Technically, that's the main conclusion. So technically, that's what we want, and that's why M delta is smooth. So let me do one more comment. At least I want to prove. So now now this statement is okay. Now I want to still consider these two statements. Recall that, so T star T times C to the K, right? It has the diagonal TK action. That's the one that we were looking at. And T star T, it simply has its standard Tn action. But because everything is abelian, so those group actions actually commute. So we have a Tn times Tk action. Then remember, we had a proposition that you were proving in the problem set in the problem set of this week, right? So if you have two commuting actions and you do reduction under one of them, the other one descends, right? So by standard wisdom, we have a Tn action, Hamiltonian Tn action. on M delta. Now, what's the moment map? That depends a little bit how we choose it, right? That's of course a little bit a matter of choice, but we can simply use this formula if we want, right? We can choose the moment map just to be given by lambda, and choose mu Tn T lambda Z equal to lambda, and then of course what we get is the by definition the image of mu Tn is equal to delta inside T star. That's the whole construction which is gauged in that way. So now I think part of the other statements is in the exercises, and instead of proving them, let me just state some big theorem. So I'll finish with a definition and the theorem. So a compact connected Hamiltonian Tn space. So let me say omega m omega mu T star is called multiplicity free if all its reduced spaces are either points or empty, right? So this is kind of this is a very strong requirement on the space, and here is the theorem, very famous theorem of Delzant, which says that multiplicity free Hamiltonian T spaces are in one-to-one correspondence with Delzant polytopes. And maybe here one-to-one, just the last words, up to an equivariant symplectomorphism intertwining moment maps, which is a natural isomorphism in the category of Hamiltonian T spaces. Right. So, so this is a very famous result. We don't prove it. However, what we do instead, right, with this construction that I showed you today, we do construct all of them, right? So Delzant's theorem says that there are no other ones. So if you have a Hamiltonian T space, it is a space as we constructed today by Hamiltonian TK reduction of the cotangent bundle of T star Tn. So this Lerman's trick, which was invented, of course, much after the Delzant's original result, but this Lerman's trick shows in rather elementary way how you can build all of those multiplicity-free Hamiltonian T spaces. And I think that's a nice point to stop. So again, next time we're going to have a kind of aside class, which is not part of the program, but which is which will be on a related topic. So it will be about Gelfand cycling systems. And our normal regular class will be in 2 weeks from now, and there we'll start doing equivariant cohomology, just to introduce yet another topic of the course. Okay, thanks a lot. I don't know whether you have questions.
If we took another character in this reduction.
Oh, instead of 0.
Yes, it's just so it seems like we just deformed this polytope, but so is
you're right. I think I had a choice. Like
it's like changing this new A's.
That's right. Instead I could have said that new A's are always I could have chosen the moment map just to be right. So here I chose the moment map to contain those new A's. But instead I could have said, no, let's take just the moment map, which is linear in lambdas, doesn't shift by any new A's, but I could have done reduction at the level equal to new A for each A. Yeah, that's of course just the same. So I chose to shift the moment map, but I could have shifted the level. You're right.
Yes,
maybe.
So is there some fun in varying this character or this new A's, or the resulting reduction will be essentially the same?
Oh, well, no, it's not going to be the same. You see, I mean, depends. Like, imagine like I'm doing something like this. Let me try to draw something. Yes, yeah, of course, I don't know, maybe I don't control my drawing well enough for it to always be Delzant, right? But let's say I have something like yeah, assume that I'm careful and everything is Delzant. Probably it's not on my drawing, but assume that I've chosen the angles well, that everything works well. So this polytope is a hexagon, and it's an intersection of 2 of 6 half spaces, right? So these are half spaces which are defined by those straight lines. And of course, in a straight line, you need a V and nu. Now, suppose I start moving one of them, right? I don't change V, I only change nu. See?
Yes.
So here it's for sure not Delzant, because there are many things to, and then you see it becomes a trapeze instead of a hexagon, and so on. So when you change nus, then there will be those so-called wall crossings. So perhaps we're gonna talk about it later in the course. So for a while, the shape doesn't change, only geometry changes, but topology doesn't change. But then there are some transitions where the topology of reduced spaces also changes. So that's one example, right? When we go through this wall crossing, then instead of a hexagon, we have a quadrilateral, in this case, a trapeze.
And this last one is Delzant again?
Oh, I mean, yes, it is. It might be, at least if I arrange. I mean, if I arrange right, I should arrange everything well, right? It might be, or maybe not. Depends on how. Like maybe in the beginning the condition got satisfied, but then it stops being satisfied. But I think I can arrange it. I may arrange it such that it's satisfied even after the wall crossing. By the way, one of the things in the next problem set is to look at the example which is not Delzant and say, what goes wrong? What happens if I took something which doesn't satisfy the Delzant condition? Then I can still do the reduction, and then what? What happens? What are the features of the reduced space which are not satisfactory, or I mean different features of the reduced space?
Really, we can take the reduction?
Sure. Oh, okay. Maybe just to say, our reduction is some kind of very, very baby reduction, in the sense that I impose conditions that everything really goes very, very nicely, very smoothly. But lots of people, they are researching on what happens if some of those conditions are dropped. For instance, especially this condition for the group, for the stabilizer acting freely.
Yeah.
That's a condition that I think in the research environment, people typically would not impose. That's it's too restrictive. So people want to know what happens if you allow some non-freeness. And then, yeah.
But then this M delta is not smooth.
Yeah, then M delta in the good cases, it's an orbifold, and in the general case, it's a stratified symplectic space. But I mean, there is a lot of already since some time, there is a lot of research, and if you just search on singular reduction at the internet, yeah, there are research conferences on singular reduction. So that's a kind of topic of research since some time, and it continues. People want to do it. Then there are kind of different approaches to it. Some people say, oh, how we desingularize? And then some other people say, no, we want to directly work with those singular spaces. Now there is all this whatever derived geometry story, and there people say no, but this is all fine, these are just good objects in our category, right? Then it starts depending on which category you're working on. There are other people who are saying, oh, those reduced spaces, they are naturally stacks, right? And then it depends. Then we kind of in the course we work in the category of smooth manifolds. And for reduction, to be honest, this is a very restrictive category. Kind of, if one wants to be a professional, one needs to choose some other category and do it there.
Okay. And maybe another question. So we have this one-to-one correspondence between these polytopes and this. So the question is, we have this Delzant polynomial, meaning we have these vectors and these numbers, but if we just look only on its combinatorics, so how can we say how this resulting reductions will be identified if we do not make difference between hexagons, for example?
So you mean if I try to choose different vectors?
I want to identify polynomials which are combinatorially the same, and what identifications will be made on another side of this one-to-one correspondence. Is it something interesting?
Wait. Say again. So we have right Delzant polytop, right? It's a polytop inside T star, and I'm able to choose, roughly speaking, let's say, to simplify things, at each corner, I'm able to choose normals to the faces, right? Each corner is an intersection for a Delzant polytop, is an intersection of exactly n faces, where n is the dimension of my torus, Tn, right? So there I'm supposed to choose normals, which would make a basis of the integral lattice. right? So I should be able to choose such normals. But I don't think there are many ways. If there is a way, it up to science, it is unique, right?
So this one-to-one correspondence.
Now again, what are on the sides of the one-to-one correspondence? On the one side are polytopes with special properties. Basically, I think if you are given a polytope, you don't need further information. Of course, this polytope is inside T star, right? And here we identify T star as a dual to the Lie algebra of our torus. So we have some integral structure already installed. So this maybe, let's say, so the two sides of the correspondence. On the one side, we have delta, which is inside T star, and T star is Lie of T star, right? So that's one part of it, and then we know something about that at each. So suppose this is a vertex of our polytope. Here I should be able to choose whatever, depending on the definition, inward or outward normals, which would form a basis of lambda, right? So I don't think so I think this choice, if it exists, it's unique. Maybe it does not exist, right? But if it exists, it's unique, right? You can always, the directions of those vectors, they are already defined, right? Then the first element of lambda, which lies on that ray, it has to be your basis vector. For sure, you cannot take the second one, because then already you lose. So that's so if it exists, the polytope already gives you those vectors, and it already gives you the news, because you know where the wall is, right? So you know that this wall has to be of the form lambda v equal to something, right? And this point, the corner, is sitting on that wall, so you actually know the new. So actually VAs and news, this is equivalent to giving you a polytope embedded into T star. So here there is just no difference in that information. So of course, not all the polytopes, they are Delzant, but if it is Delzant, then VAs and new A's, they are fixed. I don't know whether, does it answer your question?
You mean that there cannot be two Delzant hexagons? So I mean the combinatorial structure of this polytope, it gives the actual polytope with this.
No, but combinatorial structure, if you write in new, what about new? Maybe combinatorial, maybe here I'm not sure I understand you. Of course, I guess for you, combinatorial structure are VAs, right? But here we also have news. So I'm saying that the set of V's and news, which means the set of hyperplanes, is exactly the same as the polytope. So I give you the set of points, that polytope, and it uniquely tells you what were the V's and news. And of course, if I give you V's and news, you can just construct the polytope.
By combinatorial structure, I mean the set of faces and how their incidence. So I mean two hexagons are combinatorially is the same polytope.
Oh, no, but here we have considerably more information, right?
Yes.
We have polytopes embedded into T star. So it's not just a abstract polytope. So it's a polytope which is sitting inside T star.
Yes, and my question was, what if we identify two combinatorially all combinatorially same polytopes, and don't look at how they are embedded in T star? How are the resulting reductions? How are they?
I think let me make a guess. I think they are they are probably, let's say, I think they are diffeomorphic. The corresponding reduced spaces, they are, I think they are all diffeomorphic, but the but the symplectic structures are different. I think, yes, I let's say, but we'll see more of it later, but I think they are diffeomorphic, but they have different, I'm a little bit hesitant to say they're equivariantly, whether they maybe they're even equivariantly diffeomorphic, equivariantly with the torus section. Let's say maybe here I'm saying something wrong, but let's say they're equivariantly diffeomorphic, but their symplectic structures are different.
Okay. Okay. Thank you.
Okay, thank you. Thank you for nice questions.
Can I ask
all
a
right.
primitive question,
Yeah.
Anton? Sorry, it's a kind of bureaucratic question. If there was 2 or 3 pages ago, I didn't understand something that was written. Just going up 2 or 3 pages. When you stated the theorem, I think. There. Stop. I think it's here. Wait a minute.
Yeah.
There. Yeah. You have a middle, in the middle, you've written highlighted mu sub Tn of m delta equals delta. Then the line below, you say lambda in delta, blah, de blah. And at the end, you say lambda in delta I. And I'm confused about these. Where is lambda? And why do you say
but
delta?
if lambda, right? If lambda is in delta, right?
Yeah.
Then lambda is in some delta I. Delta
see.
is a disjoint
Alright.
union of delta i's.
Yes. All right. I just that's clear. Okay.
Yeah. So then we're more precise, and we're saying that.
That's fine. Thanks.
Okay. Okay. Perfect. Right. Any more questions? If not, thanks a lot. And Anfisa, could you stay for 1 more minute? All right. So people, then thanks a lot, and then see you possibly next week for this aside for the Gelfand cycling, or if not, in 2 weeks for equivariant chemology. All right. So thank you.
Thank you. Bye.
Bye.